This is lecture 2 of cryptography, and we're covering section 1.2 of the textbook. So, the primary tool in cryptography, creating and breaking secret codes, is number theory. So the first part of this course, it's basically a month's work, which means we do it all this week, because in the summer, 1 week is a month. It's just as 1 day is a week. This has to do with properties of the integers. So we have the positive integers. We have 0. We have the negative integers. And the study of the integers, of the whole numbers, is what is called number theory. And a basic concept is divisibility. So we say that the integer b divides a if there exists an integer c such that a is b times c. And the notation is b vertical line a. So when you see this notation, this means b divides a. So for example, 3 divides 6 because 6 is 3 times 2. "17 divides 68 because 68 is 17 times 4. 7 divides, I think 7 divides 1001. Why is that? Well, one way to check is divide 7 into 1001. Let's see if I can do by long division. Yeah. So 7 divides 1001 because 1001 is 7 times 147. Oops. Sorry, 143. 143. I have to do my division correctly. So 7 times 143 is 1001. So 7 divides 1001. So this notation is used all of the time in number theory. And so this means b divides a. And if we write this with a vertical, with a slash through the vertical line, this means b does not divide a. So for example, 7 divides 21, but 8 does not divide 21. So this is the basic notation. And it's really very fundamental. So there's some properties of divisibility. And this is proposition 1.4. So we let z be the set of integers. 0, plus or minus 1, plus or minus 2, and so forth. So we can say that A, B, and C be in the set Z. This is standard set theory notation, which I assume if you're taking a 400 level math class, you've certainly seen already. It just means A, B, and C are integers. And if A divides B and B divides C, then A divides C. So for example, 7 divides 35, and 35 divides 140, so 7 divides 140. And that's what this statement says. If A divides B and B divides A, the only way that can happen is if either A equals B or if A is minus B. So A is plus or minus B. And the third property of divisibility is that if A divides B and A divides C, then A divides both the sum of B plus C, and also A divides the difference of B and C. And this is something you should be able to prove as an exercise. Let me just prove the first of them. Proof of 1. If A divides B, that means that B is A times, let's say, X, for some integer X. And if B divides C, that means C is B times Y for some integer Y. So therefore C, which is BY, but B is AX, so that's AXY. So this is A times XY. And that means A divides C. That's what we wanted to prove. So this is a proof. And in 400 level math classes, proofs are part of the game. So we have to define what is called a common divisor of integers A and B is a positive integer D such that D divides both A and B. So for example, 2 is a common divisor of 6 and 10, because 2 divides 6 and 2 divides 10. Five is a common divisor of 50 and 125, because 50 is 5 times 10, and 125 is 5 times 25. So 5 is a common divisor of these two numbers. 25 is also a common divisor of 50 and 125, because 50 is 25 times 2, And 125 is 25 times 5. So the numbers 50 and 125 have 5 as a common divisor. They also have 25 as a common divisor. 25, however, is the greatest or largest common divisor, which we abbreviate as GCD, greatest common divisor, of 50 and 125. And so the definition of greatest common divisor, the GCD of two integers A and B, is the largest positive integer to the GCD of A and B. It's the largest positive integer D that divides both A and B. And the notation is the GCD of A and B is written A comma B in parentheses. So this notation always means the greatest common divisor of A and B, or sometimes written just to be very unambiguous as GCD of A comma B. So both of these notations stand for greatest common divisor. And I should say, just to be very precise, the GC of A and B, not both 0. So for example, the GCD of 7 and 0 is 7. That's the largest number that divides, largest positive integer that divides both of these two. But the GCD of 0 and 0 is undefined. So we don't talk about the greatest common divisor of 0 with itself, but it's perfectly okay to talk about the greatest common divisor of two numbers, one of which is equal to 0. So another example, the GCD of 12 and 18 is 6. We certainly have that 2 divides 12 and 2 divides 18. So 2 is a common divisor of 12 and 18. 3 divides 12 and 3 divides 18. So 3 is a common divisor. 6 divides 12 and 6 divides 18. So 6 is a common divisor. And of all of these, the largest is 6. So the greatest common divisor of 12 and 18 is 6. So for small numbers, it's pretty easy to figure out what's going on. But for larger numbers, it's not quite so easy. So suppose I take, let's say, A equal to 748 and B equal to 2024. So this is a nice example that's used in the text. And we want to find, or we want to compute the GCD of these two numbers. So one way to do it is to look at their divisors. What are the divisors of 748? Well, it's the following set of numbers. Let's say 1, 2, 2 divides it. 3 doesn't, but 4 does. 5 doesn't. 6 doesn't. So it's 5 doesn't actually. And if you just keep checking one by one by one, all the numbers up to 748, you'll see that 11 does, 17 does, 34, 44, 68, 187. 4 times 187 is 748. 374, 2 times 374 is 748. And of course, the number itself divides itself. So these are the divisors of 748. They're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of them. Huh. What about the divisors of 2024? Well, you start to check and see 1, 2, not 3 or 5, 4, 8, 11, 22, 23, wow. 44, 46, 88, 92, 184. Of course, you can always write a program, computer program to do this. Or if you use a nice program like Maple or Mathematica, there's a command to just write the divisors of the number. These are all of them. There are a lot. I mean, I'm writing down the list that's in the text. This is the example in the textbook. You know, take many pieces of paper and a pencil and give yourself some time. You can do this by hand. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 divisors of 2024. So what are the common divisors? Let's see. 1 divides both, of course. 2 divides both. 4 divides both. 11 divides both. 44 divides both. That looks like the largest. So the GCD, the greatest common divisor of these two numbers, is 44. Now, in number theory, it's very important to be able to calculate the greatest common divisor of two integers. And it's extremely important in cryptography, as we will see. And it turns out this has been considered an interesting and important problem for thousands of years. So if you study Euclid, Euclid's books contain not only geometry, but a lot of number theory. And Euclid gave an algorithm to compute the greatest common divisor of two numbers. So there's something called the Euclidean Algorithm. To compute greatest common divisors. And it's based on long division. So for example, if you have the number 230, you divide it by 7. So this goes in 3 times, 3 7s is 21. 2, bring down the 0, 7 into 20 goes twice. 2 times 7 is 14. That leaves a remainder of 6. So 230 is 7 times 32 plus 6. So this number 6 is called the remainder when you divide 230 by 7. This number 32 is the quotient. When you divide 230 by 7. The reason I have to stop at 6 is you can't divide 7 into 6. 6 is too small. So this remainder 6 is always less than what you're dividing by. And when you do long division, you divide one integer by another, you get a quotient and a remainder. And the remainder is always strictly smaller than what you're dividing by. Here we're dividing by 7, and the remainder 6 is less than 7. So in general, long division says, given integers, A and B, there exist integers, Q and R, quotient and remainder, such that A is BQ plus R, and this remainder is strictly less than what we're dividing by and greater than or equal to 0. If the remainder is 0, then A equals BQ and B divides A. So if you do long division and you get a remainder of 0, you divide A by B and get a remainder of 0, then B divides A. And if you look at the formula from the division algorithm, so A equals BQ plus R. If D divides A and D divides B, then D divides R. A is even, B is even, R is even, for example. If D divides B and D divides R, then D divides A. So the common divisors of A and B are the same as the common divisors of B and R. So we have the following very important observation. The greatest common divisor of A and B is the same as the greatest common divisor of B and R. And R is the remainder obtained by dividing A by B. This is really very important. So for example, if you let A equal to 51 and B equal to 306, and B equal to 42. If you divide 42 into 306, this goes 7 times, I think 7 2s are 14. 7 4s are 28, plus 1 is 29. That looks like it goes in 7 times with the remainder of 12. So 306 is 42 times 7 and a remainder of 12. And what this says is then that the greatest common divisor of 306 and 42 is going to be the same as the greatest common divisor of 42 and 12. What's the greatest common divisor of 42 and 12? Let's divide 12 into 42. This goes 3 times. Use the remainder of 6. So 42 is 12 times 3 plus 6. So the greatest common divisor of 42 and 12 is the same as the greatest common divisor of 12 and 6. And this we can tell by looking. The greatest common divisor of 12 and 6 is 6. So 6 is the greatest common divisor of 306 and 42. And in fact, 306 is 6 times 51, and 42 is 6 times 7. So 6 is a common divisor of these two integers. And in fact, this is the greatest common divisor. So again, in ancient Greece, it was observed that this process of successive long divisions actually gives you a method, or as one says, an algorithm, to calculate the greatest common divisor of two integers. And this is what is called, well, this is the Euclidean algorithm. Which is simply successive long divisions. So, and for those of you who are in computer science, it's a good exercise, and probably one that you have to do early on in the beginning of learning how to do computer programming. To write a computer program that implements this algorithm. So let's start with the numbers that we looked at earlier, 2024, and B equals 748. And one of the problem is to find the GCD of 2024 and 748, and not by listing, as we did earlier, every divisor of each of these two integers. Looking for the biggest one, which is very expensive in terms of time. Let's find a better way. So let's take 2024 and divide it by 748. And if we do that, we get a quotient of 2 and a remainder of 528. So then we take 748 and divide it by 528. And this goes in one time and leaves a remainder of 220. Then we take 528 and divide by this remainder. This goes in 2 times, that's 440, and leaves a remainder of 88. Then we take 220 and divide by 88. This goes in 2 times and leaves a remainder of 44. Then we take 88, divide it by 44. That goes in 2 times and leaves a remainder of 0. Now, if you look at this chain of equations, you see that the GCD of 2024 and 748 is going to be the same as the GCD of 748 and 528, which is the same as the GCD of 528 and 220, which is the same as the GCD of 220 and 88, which is the same as the GCD of 88 and 44. And the GCD of 88 and 44, you divide 44 into 88, it goes evenly. There's a remainder of 0. So this is just 44. So the GCD of these two numbers is 44. It's exactly the last positive remainder in this sequence. And this is the Euclidean algorithm. You take in, if you have two integers a and b and you want to find their greatest common divisor, divide a by b and get a remainder. Take b and divide it by the remainder, you get a second remainder. Divide the first remainder by the second remainder, you get a third remainder. You get a whole sequence of numbers. So if you write this down symbolically, it looks like this. It's supposed we let R0 be A and R1 be B. So we're taking R0, writing it as R1 times a quotient plus the remainder R2. Then we're taking R1, dividing it by R2, you get a quotient Q2 and a remainder R3. Then you take R2, you divide it by R3, you get a quotient Q3 and the remainder by R4. And the important thing is in long division, the remainder is always less than what you're dividing by. So I have A and B, I let A be the larger of the two. So R0 is bigger than R1. And when you divide by R1, you get a remainder, R2, which is less than R1. When you divide R1 by R2, you get a remainder, which is less than R2. You get this strictly decreasing sequence of numbers, but they're all non-negative. And if you have a sequence of integers that are positive and getting smaller and smaller and smaller, that can't go on forever. It has to stop after finding out how many steps. So eventually you have to get a remainder of 0. And when you get a remainder of 0, the last non-zero remainder is your greatest common divisor. That is the Euclidean algorithm. It is unbelievably important, and it is very efficient. In fact, there's an estimate for the running time of this algorithm in the book, but I'm not going to talk about that now. Now, there is a consequence of this, which is very interesting, and sometimes called the extended Euclidean algorithm. So let's just recall in the Euclidean algorithm, you take A equal to R0, B equal R1. And you have your sequence of equations. R0 is R1 Q1 plus R2. R1 is R2 Q2 plus R3. Finally, you get to a step, say A sub I minus 1. I'm sorry, R sub I minus 1 is Ri Qi plus R sub I plus 1. And R sub I equals R sub I plus 1 Q sub I plus 1 plus 0. And at some point, you hit 0 in your sequence of remainders, and your remainders are always getting smaller. And this is the GCD. Let's take a simple example. Suppose I take A to be 50 and B to be 35. So I take 50, divide it by 35, I get a quotient of 1, and a remainder of 15. If I take 35 and I divide it by 15, I get a quotient of 2, and a remainder of 5. If I take 15 and I divide it by 5, I get a quotient of 3, and a remainder of 0. So the GCD of 50 and 35 is the last positive remainder. It's equal to 5. But now I can take my 5 and I can work backwards. So 5 is 35 minus 15 times 2. But this says that 15 is 50 minus 35 times 1. Let me plug that in for 15 here. This is 35 minus 50 minus 35 times 1 times 2. That's 35 minus 50 times 2 plus 35 times 2. That's 35 times 3 plus 50 times minus 2. And what I've done is I've written 5 as some linear combination of the two numbers I started with, 35 and 50. Let me write this as 50 times minus 2 plus 35 times 3, or 5 is 50 times some integer u, and 35 times some integer v, where u is minus 2 and v is 3. So I started with the numbers 35 and 50 and 35. I found the GCD was 5, and then working the Euclidean algorithm backwards, I can write this GCD as a linear combination of 50 and 35 with integer coefficients. And you can always do this. It always works. So whenever you have your Euclidean algorithm, R0 is R1 Q1 plus R2. Finally, R sub I minus 1 equals R sub I Qi plus Ri plus 1. Ri is Ri plus 1, Qi plus 1 plus 0. So this is the GCD of R0 and R1, where you started with numbers A and B, and R0 is A and R1 is B. So this is the GCD of A and B. You can always work backwards. And we can get that the GCD of A and B can be written as the form AU plus BV. So there exist integers U and V, such that the GCD is this integral linear combination of A and B. That is what the book calls the extended Euclidean algorithm. Let me make one other important remark. If the GCD of integers A and B is 1, so for example, the GCD of 35 and 24 is 1, they have no common factor, then A and B are called relatively prime. So a pair of integers is relatively prime if their GCD is 0. Yeah. So that is the very, very, very beginning of elementary number theory, but we will see that some of the most secure codes ever invented are based on elementary number theory, of which this is an important part. That is covering section 1.2. The homework problems that are very important to them.